So for the next paper, the authors could not be with us here in person, so we have a recorded presentation for them. We won't be able to take questions live, but if you have them, you can send them the way to the authors. So let's bring up the video.
Ladies and gentlemen, good afternoon. It's my pleasure to be here today. My name is Yu Cui. I come from Zhejiang University, China. Today, I'm very excited to share our research. Distillation matters, empowering sequential recommenders to match the performance of a large language model. This work is jointly completed by researchers from Zhejiang University, OPPO Research Institute, and the University of Electronic Science and Technology of China. In conventional recommenders, we usually take ID-based historical behaviors as input and use a collaborative filtering model to capture the user preference. However, for LLM-based recommenders, we will construct users' historical behaviors into textual prompts, and then leverage a LLM to generate a response for recommendation. Owing to the inherent semantic reasoning capabilities, LLM-based recommendation methods have achieved impressive performance. As shown in the table, the representative LLM-based recommender, BigRec, has demonstrated great improvements over the SOTA conventional sequential model, EROS, on the typical Amazon games and toys dataset. Despite their effectiveness, LLM-based recommenders face serious inference inefficiency issues, posing substantial challenges to their practical applications. This motivates a crucial research question: how can we maintain the low inference latency as conventional recommenders while leveraging the excellent performance of LLM-based recommenders? To tackle the problem above, we propose employing knowledge distillation for acceleration. Knowledge distillation, KD, is a strategy that effectively transforms knowledge from a large teacher model to a smaller student model. With distilling the knowledge from a complex LLM-based recommendation model to a lightweight, conventional recommendation model, we can keep the effectiveness of LLM-based recommenders while maintaining the low inference costs. However, distillation is non-trivial in the work due to the fundamentally different mechanics between the teacher and the student models. The first challenge is the potential unreliable teacher knowledge. LLM-based models may not consistently outperform conventional models in all cases. Our empirical studies suggest that, in over 30% of cases, a conventional model could even outperform an LLM-based model, indicating that the knowledge from the teacher is not always reliable. Moreover, the LLM may encounter the issue of notorious hallucination and generate poor recommendations. For example, the LLM may recommend a movie named Iron Man Sichuan dialect, which doesn't exist in the real world. The second challenge is the model capacity gap between the teacher and the student. The recommendation mechanisms of teacher and student is quite different. As shown in the table, the overlapping recommendation space of these two models only takes a small part, indicating the huge capability gap between them. Besides, recent work on KD shows that the substantial difference in model size often makes it difficult for students to assimilate the teacher's knowledge. Given the simple architecture of the conventional models, they may struggle to fully inherit the semantic reasoning ability of the teacher, and overloading the student with teacher knowledge might impair its own ability in collaborative filtering. Besides, another challenge stems from the semantics-based divergence of teacher and student models. It's noteworthy that LLM-based models characterize the users and items mainly based on their contents, while conventional models, driven the embedding mainly from the collaborative signals. It means the teacher and student adopt entirely different semantic frameworks. Moreover, binary alignment of the semantic space for distillation could prove counterproductive. As observed in the table, two representative embedding distillation methods, hint and HTD, often perform worse than the original student model. To address the challenges of teacher knowledge reliability and model capacity gap, we introduce the importance of well-ranking distillation. The objective is straightforward. We select the highly ranked items from the teacher as a positive to guide the learning of the student, so that these candidate items can also be recommended by students. However, given that the teacher's recommendations may not always be beneficial, we introduce an importance weight that considers the following three aspects. Firstly, the position-aware weights. Consider the ranking position of the teacher model, inheriting from the ranking distillation methods. The motivation is from the ranking alignment that we would like to push a candidate item higher if the item also occupies a higher position in teacher's ranking list. Secondly, the confidence-aware weights. Aim at extracting the reliable teacher knowledge. We measure the quality of descriptions generated by LLMs by assessing the content distance between the generated descriptions and the content of the ground truth item. Thirdly, the consistency-aware weights use the model consistency between the teacher and the student to assess the importance of an instance. Our empirical studies also shows that the items that are concurrently recommended by the teacher and the student are more likely to be positive. Finally, we combine these three different ways into the distillation loss in the training strategy. To address the semantics-based divergence, we introduce the collaborative embedding distillation, which applies a collaborative paradigm to tackle the divergence of the semantic space. Specifically, we first employ a learnable projector to map the original item embeddings from the teacher to the student's embedding space to bridge the semantic gap. We further introduce a flexible offset term for each item, which is integrated with the teacher's projected embeddings to generate enriched student embeddings. Such collaborative approach allows our model to leverage the powerful knowledge of the teacher while preserving its capability to capture the collaborative signals. Here is the overall framework of the LLM to REC, which leveraged the importance of well-ranking distillation and the collaborative embedding distillation to transform the reliable and student-friendly knowledge from the LLM-based recommenders to conventional recommenders. We evaluate our method on three widely used sequential recommendation datasets and compare it with different baselines. Extensive experiments demonstrate the effectiveness of LLM to REC, boosting three typical sequential models and even enabling them to surpass the LLM-based recommenders in some cases. Ablation study shows that both distillation components are important. Removing one of them will result in performance drops. Diving deeper in the ranking distillation, we observe that developing the confidence-aware and consistency-aware ways are indeed helpful. For embedding distillation, we observe that the developed offset term is also important. Besides, we conduct additional experiments to determine the ratio of the overlapping items between the teacher and the student models. As shown in the table, the post-distillation student model can effectively assimilate the teacher's knowledge. Furthermore, it's important to note that The post-distillation student model may not entirely replicate the teacher's recommendations. Given that the potential unreliability of the teacher knowledge and the inherent teacher-student capacity gap. For hyperparameter sensitivity, the general trend is that the model's performance would increase at the beginning and then drops as the hyperparameters increase. This result validates the effectiveness of the corresponding components that each hyperparameter controls. Finally, we make a short summary. DLM-to-RAG is a novel distillation strategy to distill reliable and student-friendly knowledge from LLM-based recommenders, conventional recommenders. DLM-to-RAG leverages the importance of where ranking distillation and collaborative embedding distillation for reliable and student-friendly distillation process. Extensive experiments demonstrated that DLM-to-RAG can effectively enhance the performance of 3 typical lightweight conventional models. And now our code is available on GitHub, and we welcome you to check it out. That's all. Thank you.
Let's thank the speaker.